you want to add anything before we start, Lee?
Just thank you all for being here. I know there's a Western Conference Finals game on tonight, so if you're on watching this review instead of the game, thank you for your commitment to general chemistry. And my name's Ali, and we hope to make things easier for you today and for the exam on Saturday.
All right. All right. And for those of you that don't already know, the recording for this is going to be uploaded on the Peer Turing YouTube account. So yeah. So if you want to go back, you can always do that. All right. So let's get started. So we're just going to go over electron configuration, periodic trends, ionic compound, Lewis structures, and then we're going to break out into practice room. So I'm going to get started now. Thank you. Appreciate that. All right, so electron configuration is basically just a way for you to express where electrons are in an atom or molecule. So it can be determined, I'm sure you guys are familiar with it, it can be determined using the periodic table. And then you can also use the noble gas configuration as a condensed way to write your electron configuration. So instead of starting from the top of the periodic table at hydrogen, you would just start at the noble gas prior to, sorry, there's a bunch of questions. Okay, yeah, so you're just gonna start at the noble gas prior to the atom of interest, and you're just gonna go from there. So I'm just gonna give the example for calcium, for example. So for the regular electron configuration for calcium, you start off at hydrogen, which is in the 1s shell. You just do 1s2, 2s2, just go across the periodic table until you get to calcium. However, for the noble gas configuration, you would simply just start at argon and then go down to the next row and go from there. So I'm gonna expand on that in a little bit. If I can, there you go. So I'm sure you guys have seen something familiar. So on the left hand, let me get my pointer. You guys can see the pointer, right?
Yeah, we can.
Okay, thank you. Oh, okay. I got it. Cool. I appreciate everybody answering though. All right, so basically on the left hand side, we have our S shell. Each S shell has 2 electrons in it. On the right hand side right here, we have our P subshell. In the middle, we have our D subshell. And then down here, we have our F subshells. So first thing, so when you're trying to figure out the electron configuration for any atom, you just write the shell number, the subshell, and then the number of electrons in, that's a question for, sorry, 1 second. All right, there we go. Yeah, so you're just gonna go across, so 1s2, 2s2, 2p6, 3s2, go across 3p6, since there are 6 electrons in the p orbital, 4s2. But one thing I want to emphasize is that when you go across from 4s2, you start like this d orbital is actually the 3d orbital. So you're going to do 4s2, 3d10, since there are 10 electrons in the d orbital. And then you're going to go back to the 4th shell, so 4p6. And then same thing, so you do 5s2, but then you go back to the 4th shell to the 4d orbital, go across, and then back to the 5p orbital, then 6s2, and then once you do 6s2, you're actually going to go down here to the 4f subshell. Once you do 4f14, then you come back to the 5d orbital. So it's labeled right here, 5d orbital, and then back to the 6p orbital, and same thing right here. Awesome. So when you're doing electron configuration, and is 5d1 before 4f. So the general rule is that if you're, so I'm gonna go back. The general rule is that if you're, suppose you have an atom right here, you would do 5d1, go down, and then do 4f, whatever atom it is. However, if suppose you're looking at lead or something, you would do 6s2, 4f14, and then 5d10, and then back to 6p. Does that make sense? Cool. Yes, it does. All right, awesome. All right. So when you're doing electron configuration and electron diagrams, there's 3 rules that you need to keep in mind. The first rule is the off-off. Where are the slides for the? They're gonna be so they won't be posted, but you can always watch the recording on the YouTube channel. So there's a few rules that you need to keep in mind. It's gonna be the off-off principle. So what it basically says is that electrons fill lower energy levels before filling higher energy levels. So a violation of the off-off principle would be something like this on the right-hand side. So if you'll notice that before filling the 1s shell completely, there are electrons in the 2s shell and the 2p shell. So that's a violation of the off-off principle. Although this might happen if the electrons are in an excited state. For ground state electrons, you fill up the lower energy levels first before moving on to higher energy levels. The second principle is the Pauli exclusion principle, which basically states that no 2 electrons in the same atom have the same 4 quantum numbers. So a lot of times what that means is that if 2 electrons are in the same orbital, they need to have opposite spins. Yes. So 2 electrons, if they're in the same orbitals, so suppose if 2 electrons are in the 2s orbital, they would need to have opposite spins because um, if they're in the same orbital, their first 3 quantum numbers are exactly the same. So that's why it's necessary that the 4th quantum number, which is ms, the spin, needs to be different for the 2 electrons. Cool. All right, and our last rule is Hund's rule, which basically says that every orbital in a subshell needs to be singularly occupied before they start pairing up. So if you look right here, yeah, so if you look right here, basically what's happening here is that the electrons in the 2p orbital, they paired up before filling up singularly in each of the 2p orbital. So the correct way to write this energy diagram would be to have one of these electrons in this 2p orbital right here. Cool. Sorry, I'm trying to like look at the chat as well. But questions? I'll let the other peer leaders answer the questions in the chat. Cool. All right. Now, for electron configurations, there are 5 exceptions. And one thing I want to emphasize is that these are the only 5 exceptions. So if it's an element other than these 5, it's not one of the exceptions. So you would just do the regular electron configuration. So our first exception is chromium. And so normally we would write for the electron configuration for chromium, we would write something like argon 4s2 3d4. But since chromium is an exception, what happens is that one of the electrons from the 4s shell actually jumps up to the 3d shell, making it 3d5. So the correct electron configuration for chromium would be 4s1 3d5. So one of the electrons from the 4s shell is going to jump up to the 3d shell. And the same concept is for molybdenum. And basically what happens is that normally we would expect the electron configuration to be 5s2 4d4. But one of the electrons from the 5s shell moves up into the 4d shell, making it 4d5. Cool. And then the reason that the electron from the 4s and the 5s jump up to the d shell is because electrons would rather have either a full filled shell or a half filled shell. So when the electrons from the 4s shell jumps up to the d shell, it gives chromium and molybdenum a half filled d shell. And then the other exceptions are copper, silver, and gold. And the same thing happens, except now when the electron from the 4s or the 5s or the 6s shall jump up to the d orbital, it gives copper, silver, and gold full filled d orbitals. Cool. So a lot of times students get confused. They're like, if we were to have, suppose, so if we were to write the electron configuration for fluorine, would it be correct to say that the electron configuration for fluorine right here is 2s1, 2p6? Just say yes or no in the chat. No, right? Because it's not one of the exceptions. Although you would be like, oh, like we would want the P shell to have a fulfilled shell or whatever, but since it's not one of the exceptions, it doesn't apply. So we would just write the electron configurations how we're normally used to writing them. So it would just be 2s2 and then 2p5. Cool? Yeah, so just be careful about that. There's probably going to be answer choices on the exam that look like they could be the exceptions, but if it's not one of these 5, it's not one of the exceptions. Cool. Tungsten is not one of the exceptions, and the reason for that is because when you're doing 6s2, you actually go down to the F shell before coming back to the D shell, so it gets a little complicated. Okay. Cool. And another question you could possibly have on your exam is electron configuration with ions. So when you have cations, you're losing a valence electron. So I want to emphasize that it's the valence electrons that you're losing. And if you have ions, you add an electron to your valence shell. So in this case, this is the normal electron configuration for iron. It's argon 4s2, 3d6. A lot of students think that you would lose these. So when you go to iron 2 plus, we know that it's going to lose 2 electrons, right? But a lot of students get confused and think that the electrons are going to be removed from the 3D shell since it's the last shell that we write when we're writing our electron configuration, when in reality, you're actually losing the electrons from the valence shell. So in this case, what is the valence shell for iron? Just type it in the chat. It's the 4s, right? Like even though 3D comes after, you're still gonna lose your electrons from the 4s shell because it's the outermost shell. Cool. Yeah. So just be careful about that. You're always losing your electrons or gaining electrons in the aren't valence shells only the highest S&P shell. Yes. All right. Cool. All right. Next thing is the difference between So yes, okay, sorry. Yeah, so you would go by the highest, like mentioned, that you would go by the highest n number. So your highest n number is going to be your outermost shell. Because even though 3D on the periodic table, it comes after 4s, the fourth shell is still the outermost shell. Yeah, so even though the 3D orbital comes after 4s, your 4, like this is the third shell, this is the fourth shell. So fourth shell is still the outermost shell. Even if it does come after um, the 4s shell. Cool. Cool. Yeah, so you're asking, okay, so if it was like, suppose 4s2, 3d10, and then 4p something, you would lose your electrons from the 4p shell first, and then you would lose them from the 4s, and then you would go down to the 3d. I was answering the question. Yeah, cool. Got it. Awesome. All right, so the difference between paramagnetic and diamagnetic. So the definitions are right here, but just to go through them real quick. So diamagnetic are electrons that have completely, or they have their electrons paired, right? So it will look something like this on the right-hand side. Paramagnetic are atoms that have at least one of their electrons unpaired. So I'm gonna give you guys an example. Is chromium, let me think. Yeah, is chromium paramagnetic or diamagnetic? Just write it in the chat. Paramagnetic, right? Because if you remember our, oh, okay, nice. Yeah, so also like if I ask a question and like even if like 30 people answer it, just go ahead and answer it yourself as well. Yeah, so chromium, as we know, I mentioned before, it's one of the exceptions. So the electron configuration for chromium is 4s1, 3d5, right? So if you guys remember Hund's rule, all the electrons, they fill up each orbital first before pairing up. So that in the 3d orbital, chromium would have one electron right here, one electron right here, one right here, one right here, and one right here, and then one in the 4s shell. Because remember, it jumps up. For diamagnet, the electron pair doesn't have to be in the same square, right? It would have to be in the same square. Because each square basically represents an orbital. So there are 5 3D orbitals, and each square represents a single orbital, and each orbital has 2 electrons. So each orbital gains a single electron in each of its orbitals before it starts pairing up. So you would fill up one electron, the second right here, third, fourth, fifth, and then you would go back and you would start pairing them up. So paramagnetic electrons have at least one of the electrons that is unpaired. So even though in the fourth shell and in in 3 of the 3D orbitals, the electrons are paired, but if it has at least one unpaired electron, it's considered paramagnetic. Okay, so let me see. Is calcium paramagnetic or diamagnetic? Right. Nice. Okay. Yeah, so calcium would be diamagnetic because its S shell has both of its electrons. So since it only has one orbital, the electrons are paired. Cool. All right, so the next like major part of your exam is periodic properties and trends. So I'm just gonna, these are just things that you basically just need to memorize. So I'm just gonna go through them really fast. So group 1A, which is right here, is gonna be your alkali metals. Group 2A is gonna be your alkali earth metals. Group 6A, which is right here, is your chalcogens. Group 7A are your halogens, and group 8A are your noble gases right here. On the periodic table, periods, when I'm talking about like period 1, period 2, it refers to like the horizontal rows, and columns or groups are your vertical rows. Columns and groups tend to have similar chemical and physical properties. So nitrogen, phosphorus, arsenic, for example, they have similar chemical properties. Can somebody tell me why columns have similar chemical or physical properties? Same number of valence electrons, right? Because if you guys look at your noble gas, or I mean your electron configuration, you will realize that this is 2s1, so it has one electron in its valence shell. So yeah, so same number of valence electrons. That's why columns have similar chemical and physical properties, because valence electrons are basically what your reactions occur with. Cool. All right, so our first periodic trend, and like I like to think of it as the most important. I don't want to say important, but it's the most important that you were able to visualize your atomic radius periodic trend. So going from the top to the bottom, you're adding shells, right? So like you can guess that your atomic radius is going to be increasing as you go from the top to the bottom. But as you go from left to right, your atomic radius actually decreases. And the reason for that is because you have more protons, so they're able to pull in the electrons closer towards the nucleus, making the radius smaller. So yeah, so as you go down the periodic table, your atomic radius is increasing. As you go left to right, your atomic radius is decreasing because there's a more effective nuclear charge. Yeah. Yeah, like a few people mentioned, there's a stronger effective nuclear charge, so it's able to pull the electrons closer to itself, making the radius smaller. And on the test, you might be asked to compare ions with the same number of electrons, right? So, is there a periodic table? Okay. So on the test, you might be asked to compare ions that have the same number of electrons. So in that case, oh, I actually just wrote it. So the atom that has more protons is gonna have a smaller atomic radius, and the reason for that is because if they have the same number of electrons, but there's more protons in the center, they're able to pull in the electrons closer, making the radius smaller. All right, so the next periodic trend is ionization energy, and ionization energy basically refers to the energy required to remove electrons from a neutral atom, right? So how much energy it takes to take off a single electron from an atom. So, and like I don't know if it's obvious or not, but the more energy it takes, the more difficult it is to remove that electron. So as you go from left to right on the periodic table, your atomic radius, as we mentioned before, it decreases, right? So the electrons are closer towards the nucleus. If they're closer towards the nucleus, you can think of it as the nucleus has a stronger hold on the electrons, so it's more difficult to remove the electrons from the atom, right? So that's why your ionization energy increases as you go left to right. And you can use that same atomic radius concept to rationalize why ionization energy increases as you go up the periodic table. So as you go up the periodic table, the valence electrons, since there's less shells, the valence electrons are closer towards the nucleus. So the nucleus has a stronger hold on the electron, so it takes more energy to remove an electron. Cool. All right. Our last periodic trend is electron affinity. So electron affinity is, you can think of it like how much an atom wants an electron, or you can think of it as the likelihood of gaining an electron. The official definition for electron affinity is the energy change that results from the addition of an electron. So if there's a higher change in energy after adding an electron, that means the electron affinity is higher. So electron affinity actually follows a similar trend to ionization energy. As you go up and to the right of the periodic table, your electron affinity increases. Do we need to know electron negativity? I would say, I don't know, Ali, I'm not sure if they need to know electronegativity. I don't think so. All right. I'll move on. All right. So another concept that's slightly difficult for a lot of students to understand is second ionization energy. So second ionization energy refers to the energy required to remove the second electron from an atom. So for example, we have sodium, right? Sodium has how many valence electrons? One, right? Sodium has one valence electrons. And as we know, atoms, they want that complete shell. They want that full shell. So after you move the first electron from sodium, it has a full shell, right? So after removing the first electron, sodium has a full shell, but then you try to remove a second electron from sodium plus, it has a really high ionization energy. And the reason for that is because after sodium loses its first electron, it already has a full shell. So it really does not want to lose that extra electron and then lose its full shell. And so if you look at it, if you look at this chart right here, you'll see that, for example, for magnesium, right? How many valence electrons does magnesium have? Has two valence electrons, right? So you look at the ionization energy for removing the first electron, it's relatively small. You look at the ionization energy to remove the second electron, it's a little higher, but it's not that much higher. But then after magnesium loses two electrons, it has a full shell. And because it has a full shell, the the ionization energy to remove that third electron is really high because it does not want to lose its full shell. Cool. So just be careful about that. Look at your periodic table, figure out how many valence electrons each atom has, and based on that, you can figure out the second ionization energy, third, fourth, fifth, whatever it may be. Cool. All right. I think. All right.
Okay, so it's my turn to present to you guys some general chemistry information. So let's start off talking a little bit about what is a valence electron. Yasser did a good job explaining valence electrons are the outermost electrons in an atom. So if you have an atom, the electrons in the outermost ring, and a lot of people were asking, what is the valence electron? It's always going to be in the highest n. So if you have 5s versus 4d, or 5s versus 4f, it's whatever the highest n is. So remember the number. So 5s is going to be the valence electron. All right. So the group number will tell you how many valence electrons an atom has. Make sure you know this trick because when you do Lewis structures, you're going to need to figure out how many valence electrons a certain atom has pretty quickly. So make sure you know the group number will tell you how many valence electrons an atom has. And so with these valence electrons, what we can do is form these Lewis dot structures or symbols. And what is a Lewis dot symbol? It's just a way to represent the valence electrons around an element using the symbol to which they belong. And so uh, I've given the example of nitrogen, which has 5 valence electrons. But look at how the electrons are placed around the symbol. They're not all paired. We have a pair and 3 singles. So that's important to note because it's kind of following the Hund's rule here. We have to fill up each side before we pair electrons. And I put 2 stars by this because it's important to know this. For example, if this was written as nitrogen with 2 pairs and a dot, that would be wrong because it's not properly showing the valence electrons. So this is wrong. It would have to be the correct one that's shown there. All right, so quick detour onto ionic compounds before we talk about Lewis structures. An ionic compound is a compound between a blank and a blank. I want everyone to answer. Ionic compounds are always between a, yeah, nice, metal and a nonmetal. Good. I see someone said cation and anion. That actually works as well. So good. An ionic compound is always going to be between a metal and a nonmetal. So if you ever have to distinguish between an ionic compound and, let's say, a molecule, you know that it's going to be an ionic compound because it has a metal and a nonmetal. And so Lewis dot structures that I just talked about, they actually give us a really good clue as to what the common charges are for these ions. So if you take the example of sodium, what's the Lewis dot structure for sodium? Well, it only has one valence electron. So we're going to write one dot here. And so if we want to kind of guess what's the charge that's formed by sodium, we can look at the Lewis dot structure and realize that if we just take away that one electron from sodium, we'll have a full subshell. And so that's exactly what happens. Sodium's going to remove this electron, and it's going to become sodium plus. And so this works for pretty much any of the metals and the nonmetals. So what's important here is that these charged ions are going to combine to form a neutral ionic compound. So whenever they come together, they're going to form a neutral compound, and that's what's going to make them stable. You see, sodium wants to give away its one electron, and chlorine wants one electron really bad. So they're pretty much perfect for each other. And so sodium and chlorine, they come together. Sodium donates its electron to chlorine, and they form sodium chloride, aka table salt. And so what if it's not always as simple as sodium and chlorine charges? Okay, what if we have charges that aren't so easy to figure out? Well, we have this thing called the crisscross method. And what we do with that is if we want to combine, for example, lead and oxygen, shown on the left, we see that lead has a charge of 4 plus. Oxygen, on the other hand, has a charge of 2 minus. And so if we form an ionic compound, what's going to be the charges that they form? Well, hey, if we use this crisscross method, it's pretty easy. We just use the charge of lead and put that for the quantity of oxygen and do the same for the other way. And so we see that it forms Pb2O4, and if you simplify that, you get PbO2, and that's going to be the neutral ionic compound that's formed. If an atom wants an electron more, why would it take more energy to give it an electron? Okay, I think, yeah, okay, peer leaders are going to answer these questions. I'll just continue. Next example I have is lithium and oxygen. Lithium with a +1 charge, oxygen with a 2 minus. So we use the crisscross method, and we get lithium 2 oxygen, and aluminum and oxygen as well. For the PLTL students out there, we have this in this week's packet as an example. We have aluminum 2O3. You just using the crisscross method. I hope that made sense. Does the cation always go first? Yes. I think that's just a convention that is used. All right, so when you have an ionic compound, how do these compounds exactly come together? So we see that we have sodium ions and chlorine ions coming together, but in real life, how does that really look? And how do they form these structures? What happens is when one positive sodium ion comes with another chlorine ion, it's not just them two, it's going to be thousands and thousands and hundreds of thousands of these ions coming together to form something called a crystal lattice. And the way that works is that one sodium ion is going to be attracted to the chlorine, or let's say the chlorine ion is going to be attracted to this sodium ion in all directions. not just left to right, but also up, down, through the page, into the page, and in all dimensions. And so we have these ions being attracted to each other in all different dimensions. And what happens is we form this three-dimensional kind of array that forms into this crystal. You can think of it as kind of like a cube. So if you look at salt, everyone's seen salt. It's these little crystals and these ions. They actually come together to form this solid structure. So like it says in the slide here, ions have regular repeating arrangements called an ionic lattice. The lattice is formed because the ions attract each other and form a regular pattern with oppositely charged ions next to each other. And so it's important to remember that when you have an ionic compound, they form a crystal lattice. All right, so now we are going to get right into Lewis structures. This is the big one for this exam. This is the one that general chemistry students struggle with a lot. And so if you are struggling, hey, don't worry. This is actually one of those concepts that takes a lot of time and practice to kind of master. So, but what I've done here is I've written down these 5 steps. If you follow these steps, you will get the correct Lewis structure every single time. And make sure you follow these steps without fail. Kind of do as many practice problems as you can, and you will get these. You will get the Lewis structure right. So what's step one? Step one is always going to be, use an example while I walk through these steps. We're going to talk about carbon chloride, which is CCl4. So the first step is going to be to count the number of valence electrons. And so what does that look like? Well, it's like all the valence electrons in the molecule. We're going to have from carbon, 7 from each chlorine. So 7 times 4 is 28, plus 4, we're going to have 32 valence electrons. This is the total number of electrons. You use all the electrons. Make sure you use all of them. And to create a bond or add a lone pair, subtract 2 from this number. Okay, so step one's done. I've got the number of valence electrons. Step 2 is to draw a basic skeleton for the Lewis structure with the least electronegative element in the center, and that is except for hydrogen. Hydrogen is never ever going to be in the center of your molecule. It's never going to be the central atom. But if you want to know what's the central atom, just look for the least electronegative one, and that one's going to be in the center. So you know that that's carbon. Carbon is the least electronegative out of these two. And then I'm just going to create a basic skeleton that's going to connect all 4 of these bonds. Okay, so that's a basic skeleton. And so step 2 is done as well. Step 3, put lone pairs around the atoms until they have an octet. Start with the most electronegative atom first. And so the octet rules that each atom wants to have 8 electrons in order to be stable. Now there's a few exceptions to this that I want y'all to remember. It's hydrogen only needs 2, beryllium only needs 4, and boron only needs 6. The rest of them are going to want 8. And so if I start putting lone pairs around in order to fill up the octet, what is going to happen is I'm going to start putting these electrons around chlorine until each chlorine gets 8 electrons. And I don't need any around carbon because carbon already has 8. And so if I subtract all the electrons that I've used from this, it actually is 32. And so I've used up all of the valence electrons. And then let's say that there's a different example, step 4a. That's as if all atoms have an octet and you don't have any valence electrons left to use, then what's going to happen is you're going to place lone pairs onto the central atom. Make sure that it's in the third period or below. Does anyone know why, if atoms are in the third period or below, you're able to put more electrons than 8? Exactly, because of that D subshell. The D subshell allows you to expand the octet. and allow you to have more than 8. Now, what if you use up all your valence electrons and you don't have octet? Well, what are you going to do? We can't just get electrons out of nowhere. What's going to happen is you're going to have to make multiple bonds. You're going to change those lone pairs to multiple bonds. Now, I promise if you follow these steps, you will get the correct Lewis structure. So these steps are pretty crucial, and just practice makes perfect, okay? So again, this is just a quick reminder that if your compound has a charge, this compound right here is called nitrate. It's NO3 minus. If your compound has a charge, don't forget to add the bracket and charge because your Lewis structure is not complete without the bracket and the charge. Okay, so sometimes what's going to happen is whenever you are out of your valence electrons and you have to make a double bond in order to create octet, there's going to be more than one Lewis structure that's possible. For an example, in this structure here, the oxygen could be double bonded with this bond right here, or it could be this bond right here, or it could be this bond right here. Well, which oxygen should I pick in order to complete this Lewis structure? Which oxygen should I pick to make that double bond? Should I pick the one on the left? Should I pick the one on the bottom? Should I pick the one on the right? I don't know. What do I do? Well, here's the answer. What you're going to do is you're actually going to draw all three structures in order to equally represent each of the oxygens double bonded to the nitrogen. And what this is called is resonance. I want to tell you guys, resonance is one of those concepts that are so misunderstood in chemistry. In reality, none of these structures actually exist. Yes, that's what I'm saying. This structure doesn't exist, this structure doesn't exist, and this structure doesn't exist. So what really exists? Well, what exists is actually a hybrid of all three of these molecules, all three of these Lewis structures. What happens is, since each of these three oxygens can be picked to have a double bond, they actually all kind of share this double bond. That one double bond is equally distributed between all three of those bonds. So you can think of it as one double bond being equally distributed between three different bonds. So if you have one double bond being distributed equally, then you can kind of say that each of those oxygens has 1 plus 1/3 of a bond. I hope that made sense. So each of those bonds are a single bond plus a 1/3 of a bond. And that's what resonance is. None of these structures exist. They actually form a hybrid. Yes, 1 plus 1/3. So that is going to be going into the next concept that I'm going to talk about, and that's bond order. So bond order, it starts off pretty simple. Look, if you have a single bond, let's just say element, these aren't, I'm making these up. Let's say element X is bonded to element Y, single bond, that's a bond order of 1. Let's say element X is double bonded to element Y. That has a bond order of 2. Let's say element X is triple bonded to element Y. This is a bond order of 3. Now, are all of these 3 bonds the same? No. What turns out, a bond order of 1, or a single bond, is actually the longest bond, and it's actually the weakest bond. The second one, bond order of 2, a double bond, is a medium level with a medium level strength. And a triple bond is the strongest of the bonds, and it is the shortest of the bonds. Now, like I showed you guys, or y'all in the last example, a bond order of 1 and 1/3 is possible. And that happens through resonance. When in nitrate, you can have this double bond be distributed between these 3 oxygens equally. So that's when a bond order of 1 and 1/3 takes place. So boron needs 6 electrons and beryllium needs 4 electrons. All right, so that's bond order. The last thing that I want to talk about, oh wait, no, sorry. Oh yeah, bond order, there's one more minute. So again, this is that nitrate example. So each bond in nitrate is a 4/3 bond. That's just 1 1/3 written in improper fraction. More than a single bond, but less than a double bond. Remember, a single bond has a bond order of 1, and a double bond has a bond order of 2. So 1 1/3 actually comes between that. So if I ask you guys, or y'all, sorry, is the bond in nitrate stronger than a single bond or weaker than a single bond? Exactly, it's going to be stronger than a single bond. It's going to be weaker than a double bond. And so you can think of it as just being right in between the single bond and double bond. And there's different ways to calculate bond order. There's, some people have their own tricks. A trick that I use is I look at the molecule and I count all of the bonds that exist in that molecule. So I see that in nitrate, if I count the bonds, I have 1, 2, 3, 4 bonds. So I put a 4 in the numerator. Then in the denominator, I put how many areas are there for me to have bonds. So here's 1, and here's 1. So 3 in the bottom, and that will give you the bond order every single time. Count the individual bonds that are there, and in the denominator, just look for the domains, or how many areas are there to put bonds, and that'll give you the bond order. Now, here's the last concept I want to talk about. I don't know if y'all have gotten to this in your classes yet, but it's called formal charge. Okay, you have. That's amazing. Formal charge is this method that we use to figure out which Lewis structure is the best. That's the key. Which Lewis structure is the best? There's always going to be one Lewis structure that's the best, and we want to figure out what that is. We will use formal charge to figure that out. So each atom in the structure receives its own formal charge. So how do you calculate formal charge? What you do is you take the number of valence electrons of that atom. Let's take phosphorus, for example. Phosphorus here has 5 valence electrons. And let's look at this structure on the left first. So phosphorus has 5 valence electrons, and then you subtract the number of sticks, and then you subtract the number of dots. And so look at phosphorus. How many sticks are surrounding phosphorus? There's 4 sticks surrounding phosphorus in that figure. How many dots are surrounding it? There's actually no dots surrounding it. So the formal charge on the left would be +1. Well, what about this structure on the right? On the right, we see that phosphorus actually is surrounded by 5 sticks and 0 dots. So the formal charge on the right figure would be 0. And so we see that, okay, we can have 2 structures with 2 different formal charges. Well, which one is the best? Which one's the better structure? Well, ideally, you want each atom in your Lewis structure to have a formal charge of 0. Now, if that's not possible, try to keep the formal charges as low as +1 or -1. And at all times, you want to try to keep the central atom with a formal charge of 0. That's going to help you succeed and figure out which Lewis structure is the best. So if you have to put a formal charge on an atom, try to put negative formal charges on the most electronegative atoms. So here, in both of these options, we see that we have to put a formal charge somewhere. So we have to decide which atom should I put a formal charge on. And according to these rules, the central atom should have a formal charge of 0. And so which structure is the best in this scenario? Is it going to be the one on the left or the one on the right? Yeah, it'd be the one on the right, because we see that phosphorus has a formal charge of 0 in the structure on the right, but in the left, phosphorus has a formal charge of +1. So if we could pick, we would pick definitely a formal charge of 0. And also you see that one oxygen also gets a formal charge of 0 there. A cool trick that I want to tell you all is that if you add up all the formal charges in a structure, it will give you the overall charge of that structure. So we see that we have 3 minus 1s here. That's going to give us -3. And even here we have -1, -1, -1, and then these two will cancel. So we're always going to equal that overall charge of the ion. All right, so that's all that I have. Middle element should be 0 if you can, yes. So P has an expanded octet. Yes, it does, and that is because it's in the third period and below. So it can have more than 8 electrons. Is structures B and BE exceptions to octet being higher priority than FC? So boron, you can only really give it 6 electrons, and beryllium, you can only give it 4 electrons. What is the formal charge formula again? So that we will go back. So it's valence electrons, and this is just my version of it. There's more official versions out there, but I figured this one would probably be more easier for y'all. Is number of valence electrons minus sticks, and a stick is pretty much just a bond, minus dots, and by dot I mean electrons. So if you take the number of valence electrons, you subtract the sticks, you subtract the dots, you will get your formal charge. You don't need to know polarity for this exam. Why can you only give beryllium and boron? So that's actually a question. It's a little in depth. You should ask your professor about that one though. It's a good question, but it has to do with their like energy level diagrams and their orbitals and what they are able to hold, and they're pretty much their valence shells. Wouldn't the sticks count as 2? No, the sticks actually count as 1. So remember, it's just phosphorus here, you would subtract 4 and not 8 in this situation because there's 4 sticks. Yeah, so it can go to 8, but it's going to be satisfied at 6. Like, ideally it wants 6. So one example would be boron trifluoride. If you have boron trifluoride, we're going to see that it only has 3 bonds, aka 6 total electrons surrounding it. Yeah, if you went to 8, it would not have a formal charge of 0. That's correct. So you can actually have either of these structures. Oh, that's one question that I wanted to ask y'all. I want everyone to answer this. Is this structure on the left, this one right here, is this a valid Lewis structure? I'm so glad everyone says yes, because that is sometimes people are going to say no. That's not a valid Lewis structure. Well, hey, it is a valid Lewis structure. Just because it's not the best, it does not mean that it's not valid. So this is a valid Lewis structure. Does every atom in this situation meet octet? Yes. Do I use up all the valence electrons? Yes, I do. So it is a valid Lewis structure. But if you have this Lewis structure on the right, it's better. So yeah, both of these are valid, but this one here is the best. And we know that because of the minimization of its formal charge. Determining the best Lewis structure is based on formal charge. Yes. Let's say instead of phosphorus, the central element was carbon. Would that invalidate the structure? Well, yeah, I mean, carbon can't hold more than 8 electrons, so we can't even have the structure on the right. Do we have to draw the most correct versions, or can we draw any correct version? So usually in your test questions, you have to look out does it say which of the following is the best Lewis structure, or does it say which of the following are valid Lewis structures? So there's this differentiation between best versus valid. So just read the question, and if it says best, then they are looking for that structure with the minimization of formal charge. Does best mean most stable? Yes. Best is representing the most stable version of that molecule. Why can P hold more than 8? That's because the phosphorus actually has a D subshell. So you can expand the octet. Exactly. You do first look for octet. Make sure every atom has its octet, and then we're going to turn to formal charge in order to figure out which one is the best Lewis structure, because you can kind of think of it as octet will tell me which one's valid, and then formal charge will tell me which one's best. Exactly. It can hold more than 8 because it has a D, but carbon cannot because it's on period 2. Good job. It's period 3 and below. So period 3 and below can hold more than 8 for octet. Does sodium and Mg count? Let me just look at a periodic table real quick. So before anything, octet is number one part. Yes, like especially in future classes, you're going to see that sometimes people want to prioritize formal charge over octet, but octet is always going to be priority. If you don't have octet, it's not valid. So you need to have octet. So can period 6 or 7 hold more, even more? Well, you're not exactly going to have to have an atom, at least in general chemistry, have more than 10 electrons on it. Usually not. So don't worry about that too much. Okay, so I think I've answered a lot of questions, and it's about to be 8:30. So let's get into the practice questions. So we're going to go into breakout rooms now to do these practice questions. And so thank you guys for being in this content review set part of it. And now be prepared to be moved into a breakout room.